Please confirm you can hear me.
Loud and clear, sir. Good morning, sir.
Yes, sir, we can hear you.
Excellent. Let's dive into it. I have a hard stop by 8:30. I have another meeting after 8:30. Yeah. Right. So, thank you for those that registered for the trade call. Kicked off during the week. Others have been requesting to join, even as we have kicked off. But the kind of quality we're looking at, we will not. There's no point rushing. We're going to open another registration probably later in April. The goal is to ensure an actual transfer of knowledge or knowledge acquisition. So that is the goal. Yeah. So let's get into this. We stopped at PID. This is what I want to try to wrap up, so that in order to close this series, right, we need to finish M7, M8, M9, and M10. So we'll just devote this today to PID. You will need paper and pen, because I'll leave you to do some calculations yourself, right? So that you can have that practice, and then you take it up from there. So M1 to M4 are real fundamentals that defined the terms, the concepts, and stuff, right? So M5, we spoke about the feedback thinking, and then M6, which is very important, the process dynamics, the time constants, and we describe how process behave normally. So M7. So let's quickly get into this. The goal is to finish this, right, and walk through the quiz, right, and then you do an example, and you can now begin to build on that later. So I'll go back to the concept. Before that, let me quickly show you this. Let's can you see let me see. Okay, excellent. Now, this is a summary of the dynamics, right? We have what we call the time constant. So process types by time constant. So when the time constant is less than 10 seconds, we consider that process very fast. An example of that is flow control, pressure relief, hydraulic servo. So for those of you that have been to the field, you will be able to relate, right? Fast process, moderate process, slow process, very slow process. They have special ways by which you do their tuning, or they have a mindset or a thinking for tuning, right? So less than 10 seconds is very fast. It happens, and you can actually picture it physically. Once you open a valve, the liquid just flows out. So flow, pressure, hydraulic. Then between 10 to 60 seconds is considered moderate. So you have small vessel temperature, pressure loops, turbine speed. Between 60 to 300 seconds, it's considered a slow process. talking about large tank level, reactor pressure, right? And the slowness in this instance, of course, look at here we spoke about flow control, right? Pressure relief and hydraulic servo. Now here we are talking about large tank level. So if you have a large tank, the rate at which you fill it up. Now, for that tank that you are filling it with liquid, right? That liquid is going through a flow control process. So there is in that tank, based on what I've just said, we can identify two things. There is a level loop and there is a flow loop in one tank. Now, for the level loop in a large tank, it is considered a slow process because it is going to take time for filling to occur, right? What accessory is this? Okay. But for flow loop, once you open the valve, boom, you begin to see flow. Does this make sense to you? Please give me a thumbs up if it makes sense to you. Okay, so we have very little. So, okay, now give me a thumbs up if you understand what a loop is. Just raise your hand so that I can count. Raise your hand so that I can count. Okay, just 2 persons. Okay, four persons. Okay, so that's where the challenge is. Okay. So it's difficult to go back into that now, right? Yeah, thank you guys. You can drop your hand. It's difficult to go back into that now because I mean, we don't have the time, right? So probably what I'm going to do, okay, I don't know what to do now, but I'll think about it. Right. So and then when you have greater than 300 seconds, you have very slow process. Talking about distillation column composition, pH control, right? So those are the time constant, the speed, and the industrial examples. You see, now loop is very fundamental. I mean, it's something everybody in this class should know, right? And that is why that organized foundation training is very important. You need that foundation to build on it, right? The loop essentially is, I've shown that loop. I've shown the control loop here many times. Or probably you don't know that's what I meant by loop. The control loop consists of the sensor, the controller, and the actuator. The sensor interacts directly with the process. The actuator interacts directly with the process. The controller does not touch the process directly. Excuse me. The controller does not touch the process directly. So that is what constitutes a loop. So in a tank, for example, in this large tank, right, it is only the tank level, the level loop, that is what we consider as the slow process. But there is also a flow loop because it is flow that is causing the level to rise or reduce. And we said that flow loop is fast. Inside this tank, there could be a pressure loop. There could be a pressure loop. Inside this tank, there could be a temperature loop. Right? Quickly. So this is a course designed for so if you look at this now, can you see my screen? So if you look at this now, this is like a case study that shows how oil moves right from the reservoir straight into to the flow station, where it is separated into its component parts. Right now, if I click, so okay, this thing is not as big as it's supposed to be. So from here to here to here to here. Now, all of this in this particular tank, I did a deep dive of this tank. And here, so you see, you have the process overview, you have the normal operation, and then you have inside that tank now, you have the pressure control, right? Which is PIC 201. That is the controller. Now, on that tank also, so on that tank, you have pressure control. On that tank, you have level control, right? On that tank, you also have, okay, there is no temperature control. Okay, there should be a flow control here. Okay, I need to update this. Right, there should be a flow control. So those are the three loops working on that particular tank: pressure, level, and flow. Right? Let me go back to our subject. Okay, so I'm under pressure for time now. All right, so let me quickly run through this. Oops. Oh, what's this? Okay. Okay, so that is that. Then system-specific examples. I think, okay, so we have system-specific examples. Okay, so those are the process types. System-specific. So you have the hydropower, the loop, and then the time constant. Right? For hydropower, the gate position, the time constant is between 0.5 and 2 seconds. Hydraulic actuator responds quickly, right? Then look at in the oil refinery, the column temperature. Look at the time constant. It's between 5 to 10 minutes, right? I mean, those are very massive thermal mass in trace. So once you apply the heat, it takes time. Temperature generally is considered a slow loop, right? And then the level, approximately 25 seconds, vessel volume crude. Okay, process resist change. I'm trying to rush, and at the same time, I don't want to rush, right? So process resist change. I mean, this is just a summary, right, of the process dynamics. And the time constant is the time it takes for 63%, for the process to attain 63% of the final value, right? So the time constant measures how long the outlet takes to reach 63.2% after a step input, right? A small time constant indicates a fast loop, right? Large time constant indicates a slow loop or slow process, right? Now, from flow loops, less than 10 seconds to distill determines the tuning strategy, right? K is the process gain, and the time constant define the process. So K and time constant. So now the process gain is the ratio of the change in PV to the change in MV. We spoke about PV and MV earlier, process variable, and what's MV?
Manipulated variable.
What's MV?
Manipulated variable.
Huh?
Manipulated variable.
Okay, correct. So that is the process gain. Thank you. PV divided by MV. So together with T, it fully characterizes first order dynamics, right? Now, always run a step test. You put your process in manual mode, attain steady state, apply a step change, then record the PV, then read the time constant at 63%, approximately 5 minutes. Now, we are doing this so that you can understand. In practice, in the field, you will use a software, right? You use the software to tune the process, right? Then you match controller to process. Controller speed must match the time constants. Too aggressive will lead to oscillation. Too gentle will lead to sluggish response, right? One of the processes that frustrates is temperature loops, tuning temperature loops. Okay. Now, how to tune a process. If you can take a picture of this, it would be nice. If you can just take a screenshot of this, it will be nice. I don't want to read because this is a worked example, right? Taken out of that separator program I showed you earlier. Have you taken a screenshot? So you can, this is just 3 pages, so you can take a screenshot of this also. Temidayo raised his hand.
I'm sorry, no.
Okay. So you can take a screenshot of this, take a screenshot of this, and then take a screenshot of this. All right. All right. Okay. Now, because of the time, let's quickly do this. You probably will still need to take some screenshots too. Right. Can you see my screen? Can you see my screen?
Yes, sir.
Hello? Okay. All right. Now, this is just so because of the time, I really want to close this out, and it's I have just 1 hour, and I know that there will be questions, and I want us to I don't want to read through this, right? The concepts, the walkthrough. I want us to spend time on the simulation and the quiz, right? So that's why I'm trying to rush, right? So now let's quickly go through this. Right. Okay, great. My screen is clear, confirm. So this is what we're going to do using that simulator, right? Guide a temperature controller through 4 stages, observing each PID terms effect in isolation before combining them. So step 1, we implement P only, right? Fast but imperfect. So KP, we said K is the gain of the process. The gain is the ratio of the PV to MV, right? So we said KP equals to 2, KI is 0, KD is 0. So this is the PID, proportional gain, integral gain, derivative gain, right? So, and then you run the simulation for at least 120 seconds and observe, the temperature rises towards 60 degrees, but stops short. The gap between PV and SP is the steady state offset. And that's the downside of P only. Now, when the disturbance hits T equals to 120 seconds, the temperature drops further. P partially recovers it, but a new larger offset remains, right? So a disturbance has been programmed into the simulator to occur at 120 seconds, right? And then when you add the integral term, it eliminates the offset. So you can now see P is still maintained at 2. I, you move it to 0.1, and D, you still keep it at 0. So in this instance, for this particular loop, you are only implementing the PI controller, right? You're only implementing the PI controller, and all of those happens, right? The temperature now climbs all the way to 60 degrees. The integral accumulates and pushes the output higher, right? And then the disturbance at T120, the loop recovers fully to 60 degrees. Excuse me. The recovery takes some time. The integral is rebuilding. Now, watch out. If K is too large, the temperature will overshoot 60 degrees. The accumulated integral over pushes past set point. I will quickly demonstrate that, right? And then overshoot with K high, right? So reset and run, then observe. The temperature rises quickly, but overshoots past 60 degrees. The controller now has to correct in the opposite direction. So we model the oscillation there, right? And if the overshoot is large, the temperature oscillates before settling. So you can see that when we mention the proportional controller, the proportional term, the peculiar word we've been using was reset. When we mention the integral term, the peculiar word that we've been using is oscillation. Excuse me. So proportional introduce what we call sustained offset. The integral introduces oscillation if you are not careful, right? And have so reset and run, observe all of this, and then the configuration. When I is 0, D is 0, you have offset always, no overshoots, and it settles just before the set point, right? If you introduce the integral term, the offset will be eliminated, the overshoots will be little, right? And then it will be moderate. The settling will be moderate. And then if you increase the integral, right, you have large overshoots. It becomes oscillatory. And then if you now introduce the derivative term, you have minimal overshoots, you have fast and smooth. Right. Does this make sense to you? Okay. All right, cool. So you can, I don't know, you can take a screenshot of this if you, I mean, I think you should, I actually think you should take a screenshot of this. And then I'll just give you 1 minute to take a screenshot of that, and we'll move to the simulation and then to the quiz. And then let's get into questions and see I mean, let's do the quiz and, you know, get into the question. Okay. So that's the second page. All right. Thank you and best regards. So can you see my screen? Can you see my screen? Can anyone hear me?
Yes,
Okay.
we can see your screen.
Okay, great. Okay, so now the first thing we do is we test the P, right? KP, all right, let's even look at this. What do you think will be the implication? We have a set point, but we're not using any controller. What does that mean? Can someone quickly think about that? So you have a process like this, right? And the SP is 60 degrees, right? The error is supposed to be SP minus PV. But we set our KP to 0, KI to 0, KD to 0. What kind of process is this? Or what kind of loop is this?
I think
Someone should open the mouth and tell me. You said?
I said I think it's an open loop.
Exactly. It's an open loop. Why is it an open loop? Please, when you talk, just you just tell me your name so that we build a familiarity. Tell me your name and then answer. So why is it an open loop? Someone?
Alfred. Good morning.
Sir,
Yeah, good morning. Yeah, go on, Alfred.
Okay, so it's an open loop because there is no feedback. So the system continues. The system is continuous. We don't have any feedback we don't have any set point. We don't have any PV, and the system just continues.
No, there is set point. There is set points and there is PV. You are partially right, right? So then don't use the word continuous so that you don't get confused down the line. There is continuous process. There is batch process. and then there is a discrete process. So in this instance, it's not continuous. It is an open loop, but how did you determine it is an open loop? What makes it an open loop? Why is it not a closed loop? It's okay. Should I answer my question, or you want to help me?
Adeboye, sir.
Okay.
So because it's not applying the feedback control, it's
How?
not working. Yes, we have the set point and the process variable, but
Yeah.
since it's not applying that process variable and the set point, it's not applying the feedback we are getting, so it's not using it at all.
How is it getting feedback?
I said there is it's not working the process variable. I think there will be a sensor that will measure, but since there's no controller to work on that process variable that we have, so that's why I said there's no feedback.
Okay, yeah, you're actually correct. I'm looking for a term. The only thing that or does someone wants to try? Let me give one more person a chance. I would love it if that answer comes from you guys.
Shegun here.
Okay, Shegun.
I guess maybe because there's no error.
Simple. Thank you. That is what I'm looking for. It is the error. That is the difference between the open loop and the closed loop. Alfred, when you said continuous, you meant open loop.
Yes, sir.
Yeah. So it is the error. The reason we are constantly monitoring the PV is so that we can do this calculation, SP minus PV. And that exactly is our feedback there. The feedback of this process is that, well, you, Mr. Controller, you initiated or you sent a value of MV, manipulated variable, to the process. Normally, that manipulated variable is supposed to correct the last error that was seen. But your manipulated variable did some correction. This is the error that still remains. Then the controller will now send another MV based on this error. And that continues every scan time. That continues every scan time. I hope this is making sense to you. Thank you. This is the kind of depth I want us to be thinking about process. You look at a tank in a factory in front of you, and you begin to see all this image. Your brain becomes the digital twin of that tank, and you are seeing all the processes working. So when they now tell you that this thing is happening, they show you a symptom. You are able to quickly trace that symptom to a particular point in that loop. So even though we implemented a feedback control loop here, why is this happening? And then because of the absence of this, then this is effectively an open loop. You can do all of that in your head before even touching anything in the plants. Do you understand? That's the kind of training I got from Rockwell. Before you even get into the plants, we would have asked you 1 million questions. As a field engineer, we ask you all the questions, and we will have created an image of what the plant is like, what the problems might be, 1, 2, 3, 4. Right? We'll have narrowed it down to the first 3. And then you just go into the plant with solution. sorry, you go into the plant to confirm your hypothesis, and then you implement the solution. Okay, so that's okay. So now, when I start this process and I leave it running, you can see the PV remains okay, and then there is a process trip. So this is a safety function, right? This is safety function that has been programmed into the system. That's when temperature deviation exceed 25 degrees for 20 seconds, you need to reduce KP before restarting, right? So it's tripped the process so that no safety incident will occur, right? So let's acknowledge our reset, right? Of course, that is telling us to reduce the KP, but we don't even have any of the controller implemented. So now if I move this to 2, right? And then let me start. So let's watch. You can see the PV right there. Just give me a second. So you can see the same condition occurs, right? So let's increase the KP. So you can see the disturbance has been introduced. So now let's quickly just discuss this a bit. Or let me run this one more time and use a higher speed, right? So let me do ×2 so that it will be faster, right? And then start. So you can see how the error is trending down and the PV is trending upward. Can you see that? So take note of that. Then, okay, let's get to 120 seconds. So the disturbance has been introduced. You can see the PV dropped, right? And then you can see the error trend upwards. And then you can see the error eventually dropping back, right? So, question, what is that disturbance? In practical terms, what is that disturbance, or what could be that disturbance in a temperature control loop?
Maybe power fluctuation.
No, you tell me your name and then you answer.
Oh, Philip mentioned.
Huh? I can barely hear you.
Okay, my name is
I think I heard Caleb.
Michael. Yes, sir.
Okay.
So, the power fluctuation can cause a disturbance there.
The power condition, right?
Yes, like power fluctuation.
Power fluctuation. Okay. Any other possible cause of a disturbance? So the power, whatever that's the source of, what is giving the process temperature, right? Temperature is a measure of heat, right? So if the source of heat gets altered for some reason, it could be power. If you are not using electric power, it could be maybe the gas supply into your burner, right? Maybe so now let's assume that you are using gas. If you're using gas to generate heat and you are monitoring the temperature loop, that is the heat that is being produced, right? Now, that gas will be measured. So there is going to be a flow loop, right? A flow loop that is determining the heat. And then a temperature loop that is determining the right temperature of the process itself. So you can see the flow loop, the temperature loop rather, depends on the flow loop. So if anything, if you have any offsets on that flow loop, it's going to affect the temperature loop. Are you following? We're going to, there are, in that single sentence, there are so many practical things to unlock. In the flow loop, when we talk about a loop, when we mention a loop in automation, three things should come to your mind immediately. There is a sensor, there is a controller, and there is an actuator, right? So in that flow loop, there is a flow sensor, there is a flow controller, and then there is a flow actuator, right? Whether PCV or whatever, or FCV rather, right? In the temperature loop, there is a temperature sensor, there is a temperature controller, there is a temperature actuator, right? Now, we are principally concerned about the temperature of the process, but that process is being influenced by the flow loop. Now, that flow loop, 3 things can go wrong there. If the temperature sensor becomes faulty, if it is not well calibrated, or if it drifts, you will see the impact in your temperature loop. If there are jitters in the input cards of the flow loop controller, you will see the problem. You will see the impact rather in your temperature loop. If the valve itself is a complex equipment. So if the valve has some problems, maybe it's experiencing what we call haunting, or hysteresis, or the positioner is having problems, you will see the impacts on your temperature loop. Now, coming back to your temperature loop, you have 3 items you also have to deal with: your temperature sensor, your temperature controller, and your temperature actuator. So I'm unpacking this. I mean, we cannot go into the deep explanation, but I'm going to do it in the, I mean, for those in the class, we're going to go into the details of this, right? You cannot begin to see that it is not sufficient. I will not regard you as an automation professional, even at the basic level, if all you come to me to say is that, hey, I can program PLC. Anybody can do programming. PLC is logic. If this, then that. The real thing you are programming is the understanding of the process. That is what you are programming. That is what you are writing program for. So, for example, as a PLC programmer, you should be able to create traps for certain errors so that it doesn't affect the process. So, for example, if there is a sudden change in error, as in if there is a sudden difference in PV and MV, the ratio of PV to MV, sorry, if there's a sudden change in the error, SP minus PV, and you have a very wide gap, boom, how do you want the process to respond? This process already have a natural dynamics based on physics by which it will respond. But as an engineer, you now consider, is it safe? You can now use your engineering skills to now determine that instead of you responding proportionally, right? That is 1 for 1. Respond. That is the intelligence you now put into your PLC logic so that your process will be safe. All right. So we've done that. Let's move to the next one. Let's add the integral term. Right. So, of course, in the proportional term, we saw the sustained offset, right? So now, so you can see it has exceeded the set points, right? And then the error, so it tries to settle, then the error gets introduced, the integral term responds, right? So you can see it is going back, right? You can see the pattern. Let's make it a bit more aggressive. You can see the rate at which the correction is happening. And then you see the overshoot. So the process is at stability. So let's add the derivative term. All right. So you can see the impact, right? The D term brought the process to set points. It is the rate of change, right? So, like I mentioned earlier, when we talk about the proportional, we speak about, the next thing you likely hear is offset. When we talk about the integral, the next thing you will hear is oscillation. When you talk about the derivative, the next thing you will hear is rate, right? Because derivative is differential. It is the rate of change. Now, how does all of this impact process? There is quite a lot of things to unpack here on how it impacts process. But what I'm going to mention is this. When Ki and Kd was 0, let me just make this times 5. Let me run this again. So when Ki and Kd was 0, right, we have this process offset, right? The sustained offset. Now, as the process engineer or the system designer or the automation professional, you ask yourself, this process, can my process live with this level of offset? Right? Can I still get a quality product with 17.5 degrees error? Right? If you can, then it's just safer and cheaper for you to implement just a proportional control. But again, when you are looking at all of this, you don't look at one loop in isolation. You look at how the downstream loop impacts the loop of interest and how the loop of interest will impact the upstream loop. Does this make sense to you? Can anyone hear me?
Yes, sir. Explain that statement again.
Okay. Now, I need to find a way to be able to write. So we have discussed what loop is. A loop consists when someone mentions a loop, it's the short form of a control loop. And it is essentially what we have been modeling as the feedback loop. So that loop consists of the sensor, the controller, the actuator. Right? Now, the example I gave earlier for this temperature control loop, let's assume that this is the temperature of the fry pan. Yeah, let's use I'm doing a form project presently. I don't know when it will be finished. But let's use that example. Let's assume that we have an industrial frying pan and we are frying dodo, in mass, right? I'm not talking about these chips, plantain chips, that's easier to, but the normal plantain that is ripe and whatever. So we're frying it in mass. And we want to maintain a golden brown color. We don't want it to get to dark brown or get to black, right? So we are monitoring this temperature. And you know that if you have fried plantain before, you know that you can be frying plantain now, it is golden brown now, and you just turn your head for 1 second. By the time you are back, the thing has started burning. Meaning that the temperature gradient between, if we say that brown, golden brown is done, between done and burnt, that temperature gradient is very sharp. Once you cross that, boom, the state of the product change. Golden brown plantain is appealing. Dark brown, burnt plantain, we eat it grudgingly, but we relish golden brown. So we are using our temperature loop to monitor the temperature of the oil. We already know the set point where that oil will give us golden brown results. But that oil is not all there is in that process. There is the source of heat. Because when we get the temperature, we want to make sure we shut down the source of heat. Right? Now, there is a gas coming, supplying energy, there is a gas that we are burning. So we ignite the gas in a controlled manner in order to generate heat. Right? Now, that gas is another loop that can potentially, or of course not can, that will affect our temperature loop. So that is a flow loop. Right? Now, let's assume that we now have a robotic hand that once we reach the set point, the robotic hand will activate something like a filter that will just lift all the plantain in the frying pan up so that it will take them out of the oil. That will be the upstream loop. Is that analogy clear? Give me a thumbs up if that analogy is clear. The three loops. The flow loop, supplying gas for heating, the temperature loop, temperature of the plantain in oil, and then the robotic loop that takes out, So if your process, even though you design it to be 60 degrees, right? If your process can maintain, if this set point will not affect your process, if you feel that the product that you will get, despite this deviation from set points, is acceptable to your customer, then use a P controller. Right? Meaning that if the level of bonds or the level of burning in that plantain that will be caused by 17.5% error deviation from your set point, if that quality of product is acceptable to your customer, then you leave it at that because it is cheaper for you. I mean, the proportional controller is the cheapest to run. For example, now in a tank filling application, let's say it's a water tank in the house, and you implement a control loop, and this control loop is meant to automatically switch on your borehole. Of course, you know what the situation of power is, right? And then you went to work, and NEPA gave electricity when you were at work, so you couldn't manually pump. So then, as an engineer, you implemented a control system that if there is electricity and if the level in the tank is low, sorry, 1 second. And if the level in the tank is low, right, switch on the pump. And then your level, your controller, right, for that, you can just use a P controller because you really don't care. I mean, if you have maybe 10, 20% error, you are not particular about saying that this tank must be 90% full before you switch off. If it is 80% or 85%, you are okay with that. You don't need to implement a PI controller so as to get that precision. Does that make sense to you? Okay, excellent, excellent. Let's quickly look at this. Time is, So what does derivative action do? Now, read this and let's quickly answer it. Let's see if we can get the quiz done. Tell me. Derivative action, D responds to the current error, just like P, but scaled differently. D measures the rate of change of error, breaking the controller before it overshoots. D eliminates steady state offset by accumulating error over time. D makes the controller ignore disturbances and only responds to set point changes. So tell me.
B.
Okay. You said it. Correct. Right. So excellent. Demonstrate the offset by adding this. Let's just move on. This guy is not going to allow us to move on. Okay. Demonstrate the offset elimination by adding integral k high greater than 0. Okay. Let's quickly run this. Just hold on. I want to hack the system. Okay, something is broken here. Something is broken here. Something is broken here. Okay. Okay. All right. Let's quickly run through the quiz. What does P term mainly respond to? We have 9 questions. We can quickly finish that all the time. Yeah. Okay. So tell me, just your name and answer, quick. What does the P term mainly respond to? Past accumulated error, present error, future set point, sensor noise only.
Emmanuel,
Shegun,
I'm
present error.
present
present
error.
error.
Present error. Okay, great. Thank you, Emmanuel. Next question. If P is set to I, a common outcome is steady state offset increases, oscillation overshoot increases, the process becomes instantaneous, the sensor becomes more
Yeah.
accurate. Huh?
Steady state offset increases.
Okay. If KP is set to I, a common outcome is, steady state offset increases. No, okay. Okay, I'll know that. That's not correct. I mean, the computer is not correct. The answer is actually A. And let me just know that. I'll correct that. You understand why it is A, right?
Yes, sir.
Yeah, because oscillation and overshoots, it occurs with the integral term,
KI.
right?
Yeah.
Yes. So the
Yeah,
answer
KI,
should be
yeah.
A here. Yeah. Okay. So what does the term I, what does the I term mainly help with? Reducing noise, eliminating steady state error, that is the offset, making the process faster, turning alarms into trips.
Eliminating steady state error.
Correct.
Yeah,
Eliminating
E.
steady state error. Yeah. So when you hear offsets in process, then we are talking about the steady state error. Right. So those are terms that could be used interchangeably. Right. If Ki is too high, a common outcome is slow oscillating or haunting, perfectly smooth response, no control action, complete disturbance removal.
A.
Huh? A.
Should be A.
Or you said what? It should be
A.
Okay. Do you does anybody disagree? No.
Oh, no disagreement. A.
Okay. Okay, great. So haunting, just take note of it and go and research what it is in terms of it's a term you should know. I mean, these are things that can help you in interviews, right? So slow oscillation or haunting. Yeah, and then this term also wind up, right? Wind up. You program this. You program. You can now compensate for this in your PLC program, and to wind up, you implement that wrong. So you can begin to see why the foundation matters, right? Why it is very important. Okay, let's quickly go. What does the D term mainly do? Predictive damping based on the rate of change, accumulate error forever, replace the sensor, create steady state offset.
Predictive
Yeah,
damping
Peter,
based
A.
on rate of change.
Great. If D is too high, a common outcome is noise sensitivity and G3 output, elimination of inertia, instant settling, no response to disturbance.
Noise
A.
sensitivity.
Noise sensitivity.
Yeah. So D term can also introduce oscillation, because when your process is sensitive to noise or disturbance, then it begins to vary, quickly. I mean, deviate frequently from set points. Any slight whatever, it deviates. Any slight work, it deviates. But sometimes your process might be able to accommodate some noise, right? So that is where the difference between the engineer managing that process is. You can say, okay, you can program for that, and then, tune for that. So that, okay, this level of noise, I'm okay with it, Which are good reasons to use PID? Select all that apply. To reduce error over time, to handle disturbances more effectively, to remove physics/inertia from the process, to shape overshoots and settling behavior. Should I select A?
A, B, D.
All except C.
Okay. All
Except
except C. Okay. You said it. Okay, it's correct. A P-only controller shows 3 degrees steady state offset. Adding Ki eliminates the offset, but causes 5 degrees overshoot after disturbances. What is the correct next step? Increase Kp to suppress the overshoot faster. Remove Ki. Offset is preferable to overshoot. Add Kd to damp the overshoot introduced by integral action. Reduce the set point by 5 degrees to account for overshoot. I'm going to leave you to think about it. Take 1 minute and think about this and tell me the answer.
Okay.
Yeah, tell me.
I think C.
Yes, sir.
Sorry, say that
I
again.
choose A.
Okay, someone says C.
Yes, sir. I choose A.
And then someone choose A.
I have a
Okay,
question,
so
sir.
now, you said?
I have a question.
No, don't
Why
ask
is
me.
there no option of reducing the Ki?
Well, I don't know. You need to ask the examiner. So I am the one asking question here. So you can hold your question. Let's resolve this issue, and then you can now ask. So we have A and C, right? So the person that choose C, what would be your justification? Why do you think C is the answer? Think about what KD, the derivative action, does. Right? Think about what the derivative action does. Think about the function of the integral action, and then think about the function of the proportion controller. Will increase in Kp. So the P-only controller shows 3 degrees. The controller has taken it to 3 degrees steady state offset, right? Now you added the integral, right? It eliminates the offset, but now causes a 5 degrees overshoot. It took it over the set point by 5 degrees, right? After disturbances. Now, what is the correct next step? What will bring it back to set point? Yeah, Emmanuel.
I'll pick C because derivative is it foresees the future, so it sees that there is most likely going to be an overshoot. Then it tries to damp it before it happens. So I'm going to go with C.
No, sorry. Let me hear that. Derivative is a sort of what? What?
So it helps to, it kind of like foresees future errors based on the rate of change of the error, past errors, the rate of change of the error. So it helps to correct against future occurrences of error, something like that. So it foresees that overshoot and tries to damp it before it happens. So I'm going to go with C.
Okay. I mean, you have freedom of going with anyone.
Yes, sir.
So let's put this to a
Yes, sir.
vote.
And I
We
think
have
in addition to it brings you,
gone.
yeah, I think in addition it brings the process to steady state when we add introduce the derivative term faster as well too. So I think that makes me go for option C as well. Or another thing is would have been
Options.
to reduce KI, like I think like someone mentioned, but since we don't have that in that option, I think introducing KD it will damp the overshoot actually. So yeah.
Okay, excellent. I mean, excellent. I'm not going to get involved in this. Let's put this to vote. We have two options, A and C. So if you choose A, let me see, just raise your hand. Okay, so I have one hand. If you choose B, okay, I think, okay, Emmanuel, I don't know whether you choose A or B. Emmanuel, is it A?
Yeah, C, sir, C.
Okay, C. Okay, you choose C. Okay, so let me. Okay, so you can see the explanation. The integral action accumulates error and can drive the output past the optimal point, causing overshoots, right? So you know this exercise for me, right? It's not even about getting the correct answer, right? It is about the thinking that you are forced to do, the conflict in your thoughts that you are forced to resolve. And that helps you to walk through the process to arrive at the answer. Do you understand? And that is the purpose of these sessions, so that you can see the plant in your mind, ingest the plant, and you see big equipment. You go into Dangote refinery, you see all the equipment, and you are not intimidated, right? So that is the goal of it. At the end of the day, tuning becomes an art that depends on the process and your experience. So I don't know whether Segun has done tuning before or whatever, but your suggestion was valid. So there is not one textbook answer to a particular situation. Other options could have been here that would have been equally valid. Do you understand? Okay, excellent. I'm at the limit of my time. Let's quickly, okay, so this question 8 of 9. Let's quickly do question 9. A noisy temperature sensor causes the derivative term to drive the controller output violently, saturating the valve repeatedly. What is the correct fix? Note that a noisy temperature sensor, the derivative term, violent outputs, saturation, and it is doing it repeatedly. Of course, because the repeatedly, you can link it to noisy. Noise is not regular. So, So tell me, what would you do? Are you going to set KD to 0? Are you going to filter the PV signal before it reaches the derivative calculator? Are you going to increase Ki to override the derivative noise? Are you going to switch to manual mode and manually correct for the noise? Tell me.
The option.
Huh?
Please come again with the option.
No, it's on the screen. Can you see it?
Not yet, sir.
Yeah, sir. Okay, my own opinion, sir.
Yeah.
Yeah, so I would say option. Normally, I would have gone for option A to entirely remove the derivative action, but I think in some cases you might not just want to like entirely do that. So I would say maybe we'll go for option B. We need to filter the PV signal before it reaches the derivative calculator. Yeah. So I think that's
Okay,
my
so I have a, okay, that's your opinion. Or
yes,
that's
sir.
your, I mean, based on the options available, that's what you thought
Yes,
is best, right?
yes.
Any other, sorry, what's your name? Who just spoke?
Emmanuel, sir.
Emmanuel, okay. So any other opinion?
Well, for me, I think it will depend on the process. If the process can accommodate a bit of an overshoot, I would go with C.
You go with C, right? Increase Ki
Yes.
to override derivative noise. Okay.
Okay, for me, I think I
Any
will
other
go
opinion?
with A. Like somewhere in the last week, I said if the process can accommodate like overshoot, so just maybe PI control alone, if it can do, then we'll go with A.
Okay. All right.
Sir, I'll go with A
So
because in the last
you
class,
go with A also.
yes, in the last class, you said derivative amplifies the noise. So
Okay. Okay. I mean, yeah, I mean, you have right of going. So whether A or C or B or D. So which one am I going to click on now? But I have a question for Emmanuel. What does it mean to filter? To filter. Why did you choose B?
Yeah, I think I saw it somewhere. I can't remember when I was going through something. So, and I saw that because I think Ki, not only KD into has impact to noise. I think Ki as well. Yeah. Also is it Ki? No. Yeah. I think is it Ki or KP now. I think one of those tools can also have, but it's just that it's more significant in KD. Noise is much significant in KD, and I think also
Sorry,
in
please come again.
KI. Yeah.
Come
Okay,
again. I didn't
I'm
hear that.
saying that. Okay, I'm saying the impact of noise is
Yeah.
greatly felt in KD. Yeah, and also
Okay.
I think it's also being felt in either KI or KP. I'm not sure. I can't recall. Yeah, so that's so. But for why I chose option B, I don't have the real. I mean the explanation itself, but I think I saw it somewhere while going through something like I cannot. Yeah.
Okay, excellent. Because of the time, I advise you take a picture of the screen. In fact, don't take a picture of the options. Take a picture of this or record this answer. There is the engineering solution. There is a lazy man solution for problems like this. Right. How a technician will approach solving a problem like this will be different from how an engineer will approach it. In this sentence alone, this is a telltale, I mean, this is telling us a tale, a noisy temperature sensor. So find out what does it mean for a temperature sensor to be noisy. And this temperature sensor, the noise is showing a violent output from the controller. That is, the error is rapidly changing. What can cause a temperature sensor to be noisy? It's a lot, right? So the sensor itself, you wire the sensor into the analog inputs of the controller. Now, the manufacturer of that sensor has defined something called a settling time. That is, when you apply power and process to that temperature sensor, you need to give it X amount of time to settle. If you don't factor that in your program, in your PLC program, a perfect temperature sensor can introduce noise into your process. Does that make sense to you? Okay, now everybody's fighting me now. Nobody's talking.
Yes, sir. Yes, sir.
Okay, so now take note because of the time. In fact, someone should drop this on the chat group. We need to continue. We need to discuss this more. Take notes. Go and find out what is sensor settling time. What does it mean, right? In instrumentation. So that is the source, right? And then go and find out what PV filtering means. You implement this also in your ladder logic. I'm emphasizing all of this, not because I'm putting down PLC programmers, but my position has always been that process understanding is superior to learning PLC programming. That has always been my position. The process is not all about XIC, XIO, OTE, and all of those things, right? Those are the implementation of your understanding of the process. So let me choose this. And we have, PV filtering will solve that problem. I don't have time to unpack all of it, but someone should drop this in the WhatsApp group and let's continue the discussion there, right? And I will engage in that whatever, or you can take a screenshot of this now and drop it in the WhatsApp group, and then we'll continue that discussion there. But just at your own time, a noisy temperature sensor, find out what is that. Find out what is called the sensor settling time. Right? And this goes deeper. By the time we begin to go deeper, you now begin to say, okay, even if the sensor settling time, you have factored for it and all, what is the precision of your ADC? The ADC on your analog inputs, right? So by the time you begin to trace that thing, all the potential points of failure, you can easily over your head tell anybody this is the problem, and define it like that. Make sense? Are we good to go? So we scored 89%. Yeah, that's because of that that question too. So I'll correct that. Right. So the summary, you explain the role of PID term, you observe and confirm the steady state offset produced by P-only control, you demonstrate offset elimination by integral, you reduce offshoot derivative action, right? And then whatever. So I will give access to this sometime next week, right? So that you can come back and look at these things yourself, revise it. It's a very, very, very good knowledge you are getting. All right. So you've earned the PID engineer. So just clap for yourself, huh? If you get this, if you have understanding of this, maybe 50-60%, I think you are good. Right, because you'll just be adding blocks and blocks and blocks, and this is going to be second nature to you. And then the next thing we'll be looking at next week, we'll be looking at alarms and safety basics. Right. We'll run through this and, you know, any question? I'll just take all the time. Wow. So 2 minutes for question and then we'll shut down. Any question?
Yes, I have a question, or even two. So, firstly, when you say a loop, is it at its most elementary form that it just features only one sensor? Is it possible to have two sensors, maybe working in differential logic to give a single output for to
No,
power a loop?
no. A loop has one sensor. I'm afraid to say one controller, right? But for the purpose of this discussion, let's say one controller and one actuator. So
Okay.
in a plant, you can have, in fact, refineries, typically, they have greater than 10,000 loops. So refinery have hundreds of thousands of loops. And that's how we count it, right? That control loop, sensor, controller, actuator. So one controller can run thousands of loops. So what you look at it is that you have one sensor, you wire it to an input on the controller, and then you wire an output from the controller to the valve or to the actuator. That is what constitutes a loop. And then you have, in the documentation, you have what we call a loop diagram, right? And then your loop diagram, so you have your loop diagram. For if you have 10,000 loops, each of the loop must have a diagram, right?
All right, sir. One last question. So, when it comes to PID tuning, how is this done in a live environment? Because, of course, we'll try to eliminate the guesswork. But my major concern is, if we are trying like this, won't it be leading to loss of or wastage of resources? So, how is this done in a live scenario?
Okay, so can you still see my screen?
Yes.
Okay, so the first thing is control station is a very, very, if you can accommodate their emails, you can just register and subscribe to them. They run free webinars and some white papers. What this company does is process optimization, loop tuning. Their trainings are quite expensive. It's in thousands of dollars, right? But you can get some free information there. So I mentioned earlier that you most likely do your tuning using software, right? In the most of the DCS control system, they have their tuning application. But I showed you, so that's why I said take a picture of this. Look at this procedure. Can you see this procedure?
Yes, sir. Yes, sir.
Yeah. So just take a screenshot of it and go and read it. This is how to tune a process. Switch the process to manual, wait for steady state, apply a step change, record the response, read the value at time constant 63%. So that is find when PV reaches 63.2% of total change. Right? You know that that is the time constant, and then calculate K and then tune. Right? So that would be my answer. So just so again, you are going to use software for your tuning, but the software is as good as the person using it. Your depth of understanding, right? Your depth of understanding, So all of these are methods All of these are methods, right? Okay, Salome. Yeah, go on.
Yes, sir. My
Good morning.
question is like from that last question that
Yeah.
the option is filtering before getting to the PID controller. How do we do that in a real plant?
The PV filtering,
Yes.
yeah, it's on your logic. So I'll say take it as an assignment.
Okay, thanks.
Right. I mean, it's you do PV filtering on your so that is part of the things you now implement in your PLC logic, right?
Okay, thank you, sir.
Yeah. I mean, PV filtering is something that is actually common, right, in the process environment. So you implement that in your logic. So you find that, I mean, just do a search on PV filtering and you will see that. So any other question? So at the end of the day, you begin to realize that, okay, as an entry-level engineer, nobody will actually entrust you to go and tune a process. But when your lead or supervisor is tuning the process and you are able to contribute intelligently, I mean, of course, the accents, you don't overshine, you don't outshine the master. You respectfully contribute to what is being done, or instead of asserting, I know this, you suggest, could it be this, even though you know that you know what you're saying, right? Because the moment you begin to outshine the master, then you are causing problems for yourself. Do you understand? They say that knowledge puffs up. So you need to, what you know, you need to find a way to couch it, and how to use it. All right. Thank you, everyone, for your time today. I think we can answer. So, I mean, if you like, you can just go register with control stations and, All right. So we'll catch up again. We'll catch up again next week. And we'll continue our alarms. So once we finish this series, okay. One more, Funke, I will take that last question and then we'll close.
Hello?
Yeah.
Can you? Oh, yeah. I think I joined late too.
Okay. Yes, I think you did.
My
Congratulations.
bad, at least. And I like the last part that I made. Very nice. But I click on the previous link. Do you now have like a YouTube? Is everything on the YouTube now?
Yes, I'm trying to. So yes, I think everything was in the YouTube. My assistant is, pushes everything there.
I'm jealous hearing assistant too.
Okay,
Okay.
I understand. I understand.
Okay, please,
I understand.
can you help us push all the training, all this so far on the YouTube, so that at least let's make us, rather than watching something else, we can just burn our data using that channel. Please.
Well, I mean, so everything that's available, they'll push it there over time.
No, I'm checking the YouTube page now.
Yeah.
I know I'm there. We have only 1, 2, 3, only 5 videos there.
Okay. Yeah. I mean, that's when we started.
No,
Okay.
this is not when we started though.
No. Okay. You mean all the other ones? We'll try
No,
to.
From the very first day.
From the very first day. I'm not even sure if we
Yes.
have all the videos again, but if they are available, we'll put it there. Don't worry.
Please help
And
us
then
put it there.
those videos were not edited, or even this ones. But okay, I mean, we'll see how it goes. We'll try to.
No need of edit. Give us the raw as the class was. Just put it there for us, please.
Okay,
This is
ma.
what I've been
Okay, ma.
looking for years. Thank you. You know,
Okay,
you are
now.
still owing me.
Okay, I need to go now.
Okay, thank everyone.
Leave me
Thanks.
alone.
Bye.
Thank you very much.
Okay, bye.
All right,
Thank you,
everyone.
sir.
I thanks for your
Bye.
time. So we'll catch up next week. Yeah. Bye.
Right, sir.